In this video, we're going to finish off section 1.4 on quadric surfaces by doing example 1.4.3. This example is very similar to the one that we did in the previous video, where we're asked to name and graph a quadric surface given by its equation. This time we've got y squared minus x squared minus z squared is equal to 9. And we're going to do this by examining traces in the planes x equals k, y equals k, and z equals k for different values of k. So let's start with x equals k. And if we look at traces in these planes, if we plug in x equals k, we're going to get y squared minus z squared, and we'll bring the k over to the other side, so 9 plus k squared. So we have here coefficients that are of different signs, and so that means that we have hyperbolas in yz, and the fact that we've got different signs here means that k can actually take any value. We always have a positive coefficient over here, so k can be as large or as small. It's being squared anyway as we want. So in fact, in the x direction, we have no restrictions on k values. If we then go and look at y equals k, the planes that are parallel to the xz plane, we can plug in y equals k, and we're going to get this. So k squared minus x squared minus z squared is equal to 9. And if I rearrange that a little bit, if I move the x and z over and the 9 over, so x squared plus z squared is equal to k squared minus 9. Here we actually see we have coefficients that are both positive, and they happen to both be the same. So it is the fact that they are the same tells us that they are circles and they're both positive. I mean, an ellipse is a sort of a extra symmetric. No, a circle is an extra symmetric ellipse. So we actually, here we have circles. If you'd said ellipses, that's just fine as well. We have circles in x and z. Now, we do have restrictions. This left-hand side has to be non-negative, and so the right-hand side does as well. So k squared minus 9 has to be greater than or equal to 0, which means that k squared has to be greater than or equal to 9. So k has to be greater than or equal to 3, or k has to be less than or equal to minus 3. Lastly, in z equals k, we are going to get y squared minus x squared is equal to 9 plus k squared. Again, we have hyperbolas. In this time it's xy. We have no restrictions in this direction on k. So if we examine the kinds of traces that we have hyperbolas and circles, or hyperbolas and ellipses. So that tells us, so our traces, which are hyperbolas and circles, or ellipses, that tells us that we have a hyperboloid. Now, if we remember, the hyperboloid came in a couple different varieties. We had the hyperboloid of 2 sheets and the hyperboloid of 1 sheet. Now, of course, I said those backwards to what I was actually drawing. This is the hyperboloid of 1 sheet. This is the hyperboloid of 2 sheets. The hyperboloid of 1 sheet has no restrictions in any direction. The hyperboloid of 2 sheets does, and because we've got restrictions on k, well, that tells us that we must have the hyperboloid of two sheets. So we're going to go and graph this. So give ourselves a set of axes. There's the y and the z and the x. And so we can figure out the restrictions on k have to be sort of in this little gap here. Since our restrictions on k are in the y direction, we can figure out that this is sort of oriented on the y-axis. But we can also see this in another way. Let's examine what happens at exactly these points. Right? If we take our equation for y here, and we look what happens at exactly at k equals minus 3 or 3. If we plug in k is equal to 3 or minus 3 here, we're going to get x squared plus z squared is equal to 0. And there's only one way you can add two squares to get 0, and that's if both of them are 0. So we have x is 0 and z is 0, which means that we actually have a point. So the point 0, minus 3, 0, or the point 0, 3, 0. So on the y-axis, 0, minus 3, 0, let's put it there. 0, 3, 0 is there. And then we can imagine what happens for bigger values of k. Right? K here on the left, on the right-hand side, this is the radius, r. And as k increases, what happens if k increases? Then the radius increases. So increases in magnitude, whether it's increasing positive or negative. But for larger values of k, we get circles which are getting bigger. So I recommend, if you have circles or ellipses, that you draw those first. Those values are getting bigger as k gets bigger, right? As k goes in this direction, it's getting bigger. Same thing, if we went in this direction, the magnitude of k would be getting bigger, and so our circles would be getting bigger. They start at a point, but they're getting bigger here, and we can then fill out the shape of our hyperboloid of two sheets. And again, you can add in a little shading if you want to make it look sort of more surface-like. But that is all you need to do. That graph is as detailed as it needs to be. I suppose I could put in the minus 3 and 3 on the y-axis. But the shape and the right direction, the right orientation is what I will be looking for when you graph these quadric surfaces in three-dimensional space.